Alright, so before we move on, let's do a few concept tests here. Here is the first one. It says a point charge of 1 coulomb is placed at the center of a cube. The flux through each face of the cube is which of the following? 1 over epsilon 0, 6 over epsilon 0, 1 over 6 epsilon 0, 0, none of the above. Please talk to a person next to you. 1 minute to answer this question. The unit of the flux is whatever it is in SI unit, right? So Newton meter square per coulomb.
It says quantity of number of field that passes through an area.
Okay, it looks like there is a lot of diversity in terms of answer. I want to come back to this question in a second. I want to ask you another question, and here is the second question. Okay, the question is asking a point charge of 1 coulomb is placed off center inside a cube. The flux through each face of the cube is 1 over epsilon 0, 6 over epsilon 0, 1 over 6 epsilon 0, 0, none of the above. So the way this one differs from the previous question is that this time the charge is off center. Does that make sense to everybody? Last time it was at the center, this time it is off center. So I want you to think about this question. Alright folks, why don't you answer this one first before we discuss both answers together. You have to point at, huh? What's the number?
It's not working at all.
You have to give your name at the end to me, and I'll get this fixed also. Just give me at the end. Okay. Okay, the correct answer here is none of the above. And why is that? So the correct answer in the previous case was 1 over 6 epsilon 0, whereas here the correct answer is none of the above. Tell me why that is the case. Anybody wants to explain based upon what we had learned? If you remember, last time we talked about Gauss's law, right? And Gauss's law says that the flux, electric flux phi, this is the electric flux, this should be equal to what? The charge that is enclosed divided by epsilon 0 inside any closed surface. This is what we learned. So this is basically the statement of Gauss's law. So electric flux inside any closed surface is whatever is the total charge enclosed divided by epsilon 0. So if you have a cube, suppose you have a cube and you have some point charge sitting at the center here, what is the total flux through all sides of the cube? Will it be q over epsilon 0? It will be. And so in this case, if it's 1 coulomb, then the flux you can tell will be 1 coulomb divided by epsilon 0, the whole thing, if you put epsilon 0 in SI unit, the unit will be Newton meter square per coulomb, right? This is the flux. What do you think that the same amount of flux is passing through each face of this cube because of the fact that the charge is at the center? Because remember, flux is nothing but it's a quantitative measure of the total number of electric field lines that are passing through the surface, right? And if the total flux through this whole cube is 1 over epsilon 0 in the SI unit, then can you say that since there are 6 faces to the cube and the flux through each cube will be the same number of electric field lines will be passing through each of the phase, can you say that through each phase the flux will be 1/6 of this? You can. And therefore, the flux through each phase will be 1 over 6 epsilon 0. So that's basically what it was for the first case. Now what happens if the charge is off center? So now this time you have a situation like this where there is charge maybe over here, it's still inside but it's off center. In this case, can you still say this? Is this still true? Yeah, if I had asked you how much is the total flux through this cube with the charge off center, you would still have said it is 1 over epsilon 0 in SI unit because the charge is 1 coulomb. So this is still, the total flux through this thing is still the same because the same number of electric field lines will still be penetrating through the whole surface if you consider the whole cube. But will the flux be the same through each phase? No, the flux will be more through the phase which is closer to the charge and less through the phase which is farther away. Do you see what I'm saying? So the total number of field lines through all of the phases taken together is still going to be the same. So the flux, total flux through the whole thing is the same, but each phase now has different flux through it. And that's why you cannot say flux through each phase is the same and it is one of these things. And that's why the correct answer here is none of the above, whereas in the previous case the correct answer for this case where the charge was placed at the center of the cube was this 1 over 6 epsilon 0. Is that making sense, folks? Any questions about this? Okay, let's look at the next question here. It says Gauss's law is useful for finding electric field, and A says for all closed Gaussian surfaces, B says for highly symmetric charge distributions, C says for point charges only, D says for any type of continuous charge distribution, and E says none of the above. So please talk to a person next to you. The question is asking, when is Gauss's law useful for finding electric field? Talk to a person next to you, please.
No, but you have to have
It could be C point charge. That's what it does.
Okay, the correct answer here is B for highly symmetric charge distributions, because what you have to understand is the answer will be different depending upon, okay, because I think there are two different things here. One is Gauss's law valid? And the answer is yes, Gauss's law is always valid for any closed surface. But the question is Gauss's law useful? And the answer is no. Gauss's law is useful for finding electric field only for cases where you have highly symmetric charge distributions, such as a uniform sphere of charge, or for example an infinite sheet of charge, or for example a cylinder with charge uniformly distributed on it. Only for those kinds of problems will Gauss's law will be useful for finding electric field. Because do you see what the question is asking? Is it useful for finding electric field? Because what you have to understand is Gauss's law says this: phi is equal to q enclosed over epsilon 0. So yeah, it is, Gauss's law is always valid for any closed surface. But remember the definition of flux. Flux says this is integral E dot dA, right? And this is equal to q enclosed over epsilon 0. And let me just put a circle here showing it's a closed surface. The question is, will this law be useful for finding electric field? That's what this thing is asking. Is Gauss, when is Gauss's law useful for finding electric field? Will it be useful all the time? If I told you that here, I have a little thing here, something like this, find the electric field here due to this charge distribution here, can you choose some kind of Gaussian surface so that you can really do this integral easily? Can you? In general, no. The only time you can really do this integral easily is if there is a symmetry in the charge distribution, not this kind of case because this problem does not have enough symmetry, but for example, if you have charges on a sphere that were uniformly distributed on its surface, then I can choose a Gaussian surface. I can say, oh, if you are asking me to find the electric field at some distance r away over here, I can choose a Gaussian surface which has such a symmetry that I can actually be sure that the electric field magnitude is the same at every point on the surface, and then I can pull out the electric field so that the integral becomes trivial. Now the integral here, and if cosine theta is also pulled out, integral dA is just the area of the sphere, which is 4 pi r square. And yes, for that case you can find the electric field easily using Gauss's law. It doesn't mean Gauss's law can be useful for finding the electric field for any charge distribution. Only for highly symmetric charge distributions like sphere of charge, cylinder of charge, and infinite sheets of charge with uniform charge on them. Please.
I'm confused.
Please.
I don't understand why you can just draw a circle around something and say that that's how many charges are enclosed, and so therefore it's that over epsilon 0. I don't think that makes any sense.
Okay. I'm trying to talk about two things. If something is valid, if some law is valid, it may not be useful. Would you agree with it? So I can say, is Newton's law of motion valid? Is it a valid law? You would say, yes, it's a valid law. But if I give you a problem and I say, is it a useful law for finding something? Then you might say, no, it's not useful. You see what I'm saying? So I am saying that if suppose you have some strange looking charge distribution, suppose you had a charge that was distributed on something like this, right? And you closed this with some surface like this. It is true that Gauss's law is going to tell you that. It's going to say integral E dot dA is equal to whatever is the total charge enclosed. Maybe the total charge enclosed is Q over epsilon 0. But if suppose I ask you, can you use this law to tell me what would be the electric field here due to all these charges here? Do you think you can do this integral easily? It's not an easy integral to do because you cannot tell me, what would be the electric, you cannot tell me that the electric field is constant at every point on this closed surface. If you cannot tell me that it's constant due to this charge because there is no symmetry here, then you cannot pull this electric field outside of this integral, right? And if you cannot pull the electric field outside of the integral, then this integral is going to be a very hard integral to do. So then why would this law be useful as opposed to, say, for example, just using Coulomb's law that says, divide the thing into little dq's and add them up. So Gauss's law can be valid for any closed surface that you draw, but it will not be useful for finding electric field unless you can pull this thing out, unless you can say, hey, this integral really is this. This thing says this is integral E dA times cosine of the angle between the electric field and this infinitesimal area vector, and this is Q enclosed over epsilon 0. Now, if suppose you cannot pull this electric field out, if you cannot pull this theta out because you cannot convince me that due to all these charges the electric field magnitude is the same at every point, this integral is a very hard thing to do. How will you find that? You are supposed to do this integral to find the electric field. Do you see it's a very hard thing to do unless you can pull it out? And if there's no good argument to pull it out, it's not a useful law for finding electric field. So it's not that Gauss's law is not valid for closed surfaces, it is, but it won't be useful for finding electric field unless there is a symmetry. So you would see in chapter 23 all the problems that we will do for finding the electric field using Gauss's law will all involve very high level of symmetry. For example, uniform sphere of charge, uniform cylinders of charge, and uniform infinite sheets of charge. Those are the three problems that you can do easily by flipping your fingers using Gauss's law to find the electric field. Okay? Any questions about this, folks? Okay, then let's move on. These were the three questions that I was asking you. So the correct answer here is B. So the first thing that I want to do today is go over, oops, why is it not closing? Okay, the first thing I want to do today is go over the symmetric charge distribution cases, and the first one we'll talk about will be sphere of charge. So let's talk about electric field due to a uniform sphere of charge. In fact, we had already done it. Remember, we pretty much finished it. Today I want to focus on what about inside the sphere, but let's quickly recapitulate things that we have learned. So electric field inside or outside a sphere with uniform surface charge. And if you recall what we said last time is, if suppose you have a sphere which has a radius capital R, and suppose you are asked to find the electric field at a distance small r away, it is conventional in physics to consider the variable distances to be little r. You know, little r is the variable, you know, you can vary it. So you can ask me what is the electric field here or here or here, etc. So this is what you're asking me, and we said if we were to use Coulomb's law and the charge is uniformly distributed on the surface of this sphere, we said we would have to do a lot of work if we use Coulomb's law, because we would have to break this, all the surface charges, into little dq's everywhere. We would have to think about what is the contribution of this little dq, all of them at this point, and then add them vectorially. That would be a very hard problem. In fact, I can assure you, people in intermediate electricity and magnetism course do that integral, work that out, and it is a problem that takes a lot of time, trust me. We said we are not going to do this. We can actually instead use Gauss's law to do this problem. Okay? All of these are exactly the same statements, folks, because phi is integral E dot dA, which is this, right? So if we want to use Gauss's law, the thing that we have to really be careful about is what kind of closed surface should we be choosing to simplify our life. Because what we have to find is what is the electric field at this point produced by all of these charges taken together. If we can choose a closed surface, a Gaussian surface that helps us pull the electric field out, that helps us put this cosine theta outside, our life will be set. You know, we will have no problem, because all we have to do is integral dA, which is the total area of the sphere, which we know is 4 pi r square. So what did we say would be a good thing to do here if we are asked to find the electric field here? Anybody? Go ahead. What kind of closed surface should we be choosing? Yeah, it should be a sphere passing through this point. The point should always, the sphere or whatever surface you're choosing should always be passing through the point where you're trying to find the electric field, right? Do you remember this? Why did we choose the sphere? This is where our creativity came in, and that's what you have to do in Gauss's law problems all the time. Use your own creativity to think of a surface, and this is an imaginary surface. This surface here is what we call a closed surface or a Gaussian surface or an imaginary Gaussian surface, because this is not a real thing. This is a trick that we are using to find Gauss's law, to find the electric field, because we want to choose any closed surface that will make our life easy. Now what we said last time is that, hey, since this sphere is concentric with this, from the symmetry of the problem I can say for sure that at every point on this sphere the electric field produced by all of these charges taken together will exactly be the same. Would you say that, the magnitude of electric field from the symmetry of the problem? Okay, good. The other thing we said is that the direction of the electric field at any point, say over here, it cannot be like this, it cannot be like this. From the symmetry of the situation, the way things are symmetrically situated, the only way it can be is along the radial direction, right? So we have one thing, we already know electric field at this point should be radial this way, electric field say at this point on this Gaussian surface should be radial this way, etc. If that's true, what is the angle between the electric field and the area vector? Somebody from here, what is the direction of area vector at this point? Little dA? Which direction is it? Very good. It is also in the same direction as the electric field, because area vector is always perpendicular to the area, and for a closed surface you always choose it to be outward perpendicular or outward normal, right? So, and similarly, if I asked you what is the direction of the area vector dA here, infinitesimal area vector, you would say it is outward normal again, and that is the same direction as the electric field. So the angle between the electric field and the area vector then is 0, and cosine 0 is 1. So what we said last time, let me pull that. So what we said is that we have this E times cosine 0 degrees times integral dA magnitude over this whole Gaussian surface that we have chosen should be equal to Q enclosed, which is the total charge. Let's say that the total charge adds up to Q, okay? So it's capital Q, total charge enclosed, let's give it a name, capital Q, and integral dA is the total area of what? I want somebody from the last row to say this integral dA is the total area of the real sphere on which the charges are, or the hypothetical or imaginary Gaussian sphere that you have chosen because you have been asked to find the electric field at a distance r away. Which of these is it? Please.
The Gaussian one?
Excellent. It is always going to be the area of the Gaussian sphere, because the thing is you are talking about the finding the electric field at this point. So the sphere that we are considering right now is this sphere, right? Because we want to know what is the electric field at a distance small r away. Is that making sense? So this thing will be 4 pi small r square, right? Is that making sense? So this will be E, and cosine 0 is 1 times 4 pi r square. This is equal to Q divided by epsilon 0. Please.
So if it wasn't like a Gaussian surface, then you wouldn't pull the cosine out of the integral? If it wasn't the same angle of the...
Yeah, suppose you said, I am not going to choose my Gaussian surface to be a concentric sphere with this thing. Suppose you chose your Gaussian surface to be like this, some strange looking thing like this. Will you still say that this equation is still valid, this equation or this equation or this equation? Yeah, they are all valid because it's valid for any closed surface, right? So Gauss's law is still going to be valid, but the question is it useful for finding electric field? Can I say that the electric field can be pulled out of the integral for this Gaussian surface? Is the electric field constant everywhere? It is not. So I can't pull the electric field out of this integral because the electric field magnitude is not constant everywhere on this surface. So that surface is not going to make my life easy, because what I'm fishing for is this. I'm fishing for the electric field. Gauss's law does not have the electric field itself. It has flux, which depends upon an integral of electric field. So unless somehow you can make your life easy by pulling this electric field out by choosing some clever Gaussian surfaces, it's not going to be useful for finding electric field. So this surface is not a useful surface to choose to find the electric field due to this sphere of uniform charge, but a concentric sphere is useful, because then I can guarantee you that the electric field magnitude is the same every point. I can pull it out, I can guarantee you about the angle, pull it out, and we are left with electric field magnitude is equal to Q divided by 4 pi r square times epsilon 0. And notice that this thing can be written as E is equal to K Q over r square, where K is the constant we talked about. This is 1 over 4 pi epsilon 0. Remember this? This was 9 times 10 to the power 9 Newton meter square per Coulomb square. Do you remember that? Okay, so what is the conclusion? Can somebody summarize the finding in plain English? What is the magnitude of, what is the electric field due to a uniform sphere of charge at any distance r away? You know, this could be here or here or here or here, 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 so long as the r is out, the point is outside where we are finding the electric field. Do you see we can use the same logic? If you had asked me, tell me the electric field at this point due to this sphere of charge, what would I have done? Should I have chosen a Gaussian sphere passing through this point? Sure. Will I have used the same logic to come to this conclusion? The only difference is this r here is going to be this distance r, right? But the same logic applies. So what is the conclusion? Anybody wants to tell me, is this looking extremely familiar, this expression? What does it remind you, please?
It just shows that the electric field decreases with increasing distance from the original charge.
Excellent, that definitely is true. So one thing you can see is that as you go farther and farther away from the sphere, so long as you are outside the sphere, the electric field is decreasing as 1 over r square. That's true. But you know, this is exactly the same expression that we had for, yeah, for electric field due to a point charge. Remember? Electric field due to a point charge, wasn't that also equal to kq over r square? And now we are saying that electric field due to a uniform sphere of charge, where charges are uniformly distributed all over the sphere, looks exactly like the electric field due to a point charge, so long as you're looking at a point outside the sphere. So to summarize, electric field produced by a uniform sphere of charge outside the sphere is the same as electric field due to a point charge at the center of the sphere. So in pictorial form, this is what I'm saying. I'm saying if you have uniform charge that adds up to Q, the total charge here is Q, and you have to find the electric field at a distance r away, this is exactly the same as if all the charge was just a point charge here and you were looking at electric field at a distance r away. Do you see what I'm saying? In these two cases, the electric field is exactly identical because the electric field will be radially out from here, it's radially out from here, and the magnitude of electric field in both cases is kq over r square. By the way, if the charges were negative, how would the results change? The magnitude will stay the same, but the direction will just become radially inward, right? Okay, so far we have talked about the electric field outside a sphere of charge. Let's now talk about inside. If we are talking about what is the electric field inside this sphere with uniform charge on its surface, suppose I asked you what is the electric field here? What would you do? Any thoughts? If I wanted to use Gauss's law, what kind of Gaussian surface would be a useful Gaussian surface to choose? Somebody from the second line, please. Again, sphere. Sphere would be the right thing to choose. Let me just remove this thing. So now we are focusing on electric field inside. This, we are done with outside, so now we are going to focus on inside. And inside, the point that I'm focusing on is at a distance small r, because small r is going to be our variable. This is where you have to find the electric field, and as he correctly pointed out, we should again choose our Gaussian surface to be a sphere, which should be passing through the point where you're trying to find the electric field, right? Does that make sense? Now again, without doing any work, is everybody going to be willing to bet? By the way, charges are uniformly distributed. I cannot show it on the picture, but charge is uniformly distributed on the surface of the sphere. Will everybody vouch to it that the electric field magnitude must be the same at every point on this Gaussian imaginary surface that we have chosen due to all these charges on the real sphere? You know, from the symmetry of this problem, can you see that this point has exactly the same symmetry with respect to these charges as this point or any other point, right? Do you see that? So because of that, again we can say, hey, we can pull the electric field out, right? The other thing, what can we say about the angle? Again we can say the same thing, that the electric field at different points here, you know, it couldn't be due to all of these charges taken together, it cannot be this way. It just doesn't make sense for electric field to be that way or this way. The electric field can only be along the radial direction. So over here the electric field couldn't be like this, or it couldn't be like this. This wouldn't make sense, because if it could be like this, then why couldn't it be like that? Right? Because the charges are uniformly distributed. This uniform charge, whatever it does, it will produce, if it produces an electric field at all, it better be along the radial direction. Do you see? So the best bet will be, you know, you choose radial direction, either out or in, doesn't matter, but the point is it definitely is going to be radial. Is the logic clear that this is just symmetry argument? If those two arguments are true, I can pull the electric field out, I can pull this thing out, and again I have the same exact thing, E times this times integral dA is equal to, let's give it a name, Q enclosed divided by epsilon 0. Is everybody seeing? All I'm saying, let's use Gauss's law, pull the electric field magnitude out, because everywhere the electric field magnitude is the same on our imaginary surface. Cosine of the angle is again the same. Why? Because if it's radial, the electric field is radial, dA is radial, so electric field and dA are pointing in the same direction. In a second we are going to see that electric field actually turns out to be 0 everywhere. There is no electric field. But if it was non-zero, then it will be pointing radially. There's no other direction. Okay, so now is everybody seeing that this logic applies? Again, the area of this Gaussian sphere is 4 pi times this variable r square, right? 4 pi r square, and this thing we should call Q enclosed. This thing we should call Q enclosed. So this is the electric field at any point a distance r away from the center. Now the question is, what is Q enclosed here? How much is the charge enclosed by this Gaussian surface if you're looking at a point inside the sphere on which the charges are? Yeah, go ahead. It'll be 0 because there is no charge enclosed here. This is the charge this is the region that we are interested in, because this is my Gaussian surface. Do you see there is no charge enclosed inside? All the charges are outside. So is everybody convinced that Q enclosed is 0? Okay, so but since Q enclosed is 0, that means the magnitude of electric field is 0. So what conclusion have we come to? Could we have chosen this point to be anywhere, not just here? We could have chosen it to be here. If we chose this point to be here, we should have drawn a Gaussian sphere here. But again, do you see Q enclosed would have been 0? If we had chosen a point, if you asked me what is the electric field here, I could have chosen a sphere passing through that point. If you had asked me for electric field here, I could have chosen a Gaussian sphere passing through that point, right? But do you see that the logic still carries through? In the end, since there's no Q enclosed, the electric field is 0. So what conclusion have we come to in plain English? That the electric field, due to a uniform sphere of charge at any point inside the sphere, is 0. Look how beautiful Gauss's law is. We did not do any complicated integral, nothing. In Coulomb's law, you could not even have convinced yourself, if suppose I asked you, prove that the electric field here is 0 by taking little dq's here, little dq's all over the place and adding up their contribution, you would have taken, half an hour or 1 hour to do the calculation, and even then you would not have been convinced that if the electric field turned out to be 0 here, it will be 0 here, 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 everywhere. But Gauss's law is showing it has to be. There's no other way. So it's such a beautiful argument based upon symmetry that the electric field everywhere inside a sphere of charge on which charges are distributed uniformly on the surface must be 0. Okay? So what we are saying is electric field inside a sphere with uniform charge on the surface is 0. So if we had to make a graph, suppose in the exam, one of your questions is saying choose which of these graphs is the correct graph for electric field with uniform charge on its surface, and it shows the electric field inside and outside. I want all of you to talk to a person next to you, take 1 minute and tell me how to draw a graph. So all I want you to do is this: draw a graph of electric field along this axis. This is the magnitude of electric field, this is your variable r, this is the radius, r is equal to r. Tell me what this plot will look like. Everybody should be talking to a person next to them. So graphical representation of what we have found about electric field inside and outside. Please talk to a person next to you. Alright folks, anybody wants to help me? How about second row? Somebody from the second row? Go ahead please.
It will have to be 0.
So it has to be 0 all the way from here to here?
Yes.
And then?
It'll reach its maximum value.
Okay.
And then, at, like a like a parabolic decay, or like a
1 over r square, right? Very good. So the thing is, what he's saying is absolutely correct, which is that the electric field will have to be 0 everywhere inside from the center here all the way till the point where we reach the radius, or everywhere 0 0 0 0 0 all the way till here. As we go to the surface, the electric field suddenly jumps, and what will the electric field be here? The maximum value will be E is equal to k q divided by r square, where r is the radius, because remember that's the distance here. This is the capital R, this is the radius of the sphere on which the charges are, and then as you keep going out, the general form of the electric field magnitude here is going to be k q over small r square. Small r is the variable, right? Is that making sense? It will fall off as 1 over r square outside. Now notice that there is a discontinuity in the electric field here. You know, so if you go from outside infinitesimally close to the surface, so long as the charge is enclosed still, the electric field will be kq over r square. If you go from inside infinitesimally close to the surface, so long as the charge is not enclosed, it's going to be 0, and suddenly the electric field will jump from one value to the other. Is that making sense? Please go ahead.
Will the parabola ever reach 0, or is it like an asymptote?
Oh no, it will reach 0 at r going to infinity, right? So you can see that as r goes to infinity, you can see E, which is equal to k q over r square, this will become k q over infinity square, which goes to 0, right? 1 over infinity is 0, so it will go to 0 eventually very, very far away. So if you can say, oh, r is extremely large, it's almost infinite. What is infinite? Nothing is infinite, even the size of the universe is finite. But the thing is, infinite just means extremely far away compared to the distance on which the charges are distributed. You know, so if suppose your radius is r, this capital R, and you go very far away compared to r, maybe 100 times r, this r, you can already call it infinite. Do you see what I'm saying? Okay, any other questions, folks? Okay, so then before we move on, I want to do another problem, and this time we will have electric field due to a sphere on which charges are uniformly distributed everywhere inside. So for example, you could have an insulator, a yarn, think of a yarn ball, and if there was charge everywhere inside this yarn ball, how would the electric field differ at different points? You know, can we figure out what is the electric field? So let's do electric field due to a uniform sphere with volume charge. So, and we are going to assume that rho is what is called charge per unit volume, or we can call it charge density. Suppose if Q is the total charge, and R is the radius of the sphere, who wants to tell me how to relate Q with rho and R? So here is your sphere. This time there's charge uniformly distributed everywhere in the volume. This is the radius R, total charge is Q, Q is the total charge, and rho is the charge in unit volume. So if you look at unit volume, 1 meter cubed, the charge in 1 meter cubed is rho. Another 1 meter cubed, rho. So rho is the charge per unit volume. Who wants to tell me the relation between these three things? Go ahead, please. Q is equal to rho times what?
4/3 pi r cubed.
Very good. It will be Q is equal to rho times the volume of the sphere, right? And as she correctly points out, volume of the sphere is 4 over 3 pi r cubed, right? Is that making sense? Okay, so here are two things again. We want to know what is the electric field outside this and what is the electric field inside this at some distance which is variable r. So let's first do outside. Outside is going to be really easy. So if suppose we want to find what is the electric field at a distance r away, this is my r. Again, is it clear to everybody from the symmetry of the situation that if I want to find the electric field here, I should choose a Gaussian surface that is passing through here, and that should be a sphere, right? That has this right symmetry so that we can pull the electric field out. Okay. So if that's the case, let's choose, this is my imaginary Gaussian surface. Okay, so if that's my imaginary Gaussian surface, can we again make use of Gauss's law? Yeah, let's make use of Gauss's law. First of all, can you argue that the electric field at every point on this imaginary Gaussian surface that we imagined must be the same due to all these charges that are uniformly distributed here? Yeah, we can, because again, if just think about the symmetry, if you look at this point with respect to all these charges on the sphere which are uniformly distributed, this point is no longer, you know, and not any special compared to say this point with respect to this whole sphere, or this point or this point or this point. They're all on the same footing, right? And if that's the case, we can again say the magnitude of electric field better be the same everywhere. Not only that, what about the direction of electric field due to all these charges? Can I say to you, can I convince you that the electric field at this point will be at 30 degrees here? No, because then you will say to me, if the electric field is in this direction due to all of these charges on the sphere, why couldn't it be at 30 degrees, say this way? Right? So again, the point is that there's so much symmetry here in terms of how the charges are distributed on the sphere that you have to convince yourself that the electric field at this point has to be radial. That means straight out from the center. There's no other possibility for electric. If you ask me electric field at this point, I would say it has to be radially out. It cannot be this way or that way. And so we again have the same kind of thing. We know that the electric field magnitude at every point on our imaginary Gaussian surface must be the same, so we can pull this out. We know that cosine theta is again cosine 0 because the angle, if you think of the dA here, dA is always outward normal for a closed surface, so dA and electric field are in the same direction there. You know, if you're thinking over here, again the electric field will be radially out, dA will be radially out. So the point is dA and electric field are both pointing in exactly the same direction, and so this is cosine 0, which is 1. So is everybody seeing that this logic again applies? Doesn't that? Do you even want me to write down, or is this good for everybody? Let me write it down. All I'm trying to say is that this logic is still good for this problem so long as we are finding the electric field at some point here, and we can again say, oh, I'll pull out here is where we are starting, we'll pull out the electric field, we'll pull out cosine 0 degrees, which is 1 anyway, and this becomes integral dA over our closed imaginary surface, and this is equal to q enclosed divided by epsilon 0. So this will be cosine 0 is 1, this is 4 pi times the radius, variable radius of this Gaussian sphere square, and this is equal to q enclosed over epsilon 0, or the magnitude of electric field is q enclosed divided by 4 pi r square epsilon 0, or electric field is equal to k q enclosed divided by r square. Now here is the question for you. What is Q enclosed so long as the point is outside? You know, look at this point. We chose this point to be outside this yarn ball, right, on which the charges were distributed. So what is Q enclosed, folks? Somebody from the fourth row. Q. It is the total charge Q. Everything is enclosed. Do you see that? So that's excellent. So the point is that for a point outside, so for r greater than the radius of this yarn ball, that means for a point outside, we have Q enclosed is equal to all of the charges Q, and so our electric field magnitude then turns out to be K Q over R square. Right? Hey, is it again like a point charge? Is this whole volume of charge behaving as though it was just a point charge? Yeah. So what we are learning is that for a point outside, so long as R is greater than R, this whole ball may have charges uniformly distributed so that Q total is Q. And if you are looking at a point at a distance r from the center, the electric field at this place has a magnitude K Q over R square. It's radially out, and it is just as though all of these charges were just at a point, and the electric field obviously is going to be radial in this case also, and its magnitude here is given by the same expression. Is everybody understanding that for a volume distribution of charge also, so long as the charge is uniformly distributed inside the volume, if you're finding the electric field at a distance r from the center, it's going to be exactly like the electric field due to a point charge. What about the point inside now? So now change the problem. Is there any question about this, anybody? Okay, so then now let's try to find the electric field not outside, but let's try to figure out what would be the electric field, say, at some point inside. Let's say over here at a distance r away. What should I do now? Should I choose a Gaussian sphere again passing through this point where you have asked me to find the electric field? Yeah. So if you have asked me what is the electric field here at this point, I will choose a Gaussian sphere My spheres are not looking like spheres, right? Looking like ovals. Okay, so this is my Gaussian sphere. This is my imaginary Gaussian sphere. Okay, again, from the same argument that we had used earlier, can we say that, look at the way the charges are distributed on this sphere. Will you be able to say that every point here has the same symmetry as every other point? In other words, I cannot say this point is more special than this point or this point or this point. If they all have the same symmetry with respect to how the charges are distributed here, won't the electric field magnitude be the same at every point here due to all of these charges? Do you see that? So again, from the same kind of argument, you can say that if I were to find the electric field magnitude here due to all these charges here, 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 all of them should give me the same magnitude electric field here as, say, for example, some point here or here or here or here, because the charges are symmetrically distributed in a way that no point on the sphere has any special preference. Right? Is that clear to everybody? The second thing to realize again is, what about the direction of electric field? Does it have to be radial again? Yes. So the thing is, electric field at this point has got to be radial, either this way or inward, but the thing is it cannot be at 30 degrees or 60 degrees or 45 degrees this way or that way, because otherwise you can again say, why is this direction preferred over this direction when the charges are uniformly distributed like this? There's no reason to prefer one direction like this versus the other. So the only possibility is electric field is radial. Okay? If that's the case, can we again start with Gauss's law, again go through the same argument and say we can pull the electric field out if the magnitude of electric field at every point on the Gaussian surface is the same. Cosine theta is cosine 0. Integral dA will again give me 4 pi r square. This time what is r? R is this radius this time, right? It's a variable. So 4 pi r square will give me the area of that sphere, right? The surface area of that sphere, and I again get exactly here. Do you see that all of this will still be good? The only question that we come to now is what is, let me erase this now. The question is what is Q enclosed? And it's not very hard to find. This time it's not 0. Notice Q enclosed is not 0. So for r less than r, that means for a point inside the sphere, the question is it possible to find Q enclosed? How do you think we can find Q enclosed? Do you notice that there's some charge that is enclosed inside here? All this charge is enclosed, but all this charge is not enclosed. Is everybody seeing that we need to somehow figure out how much is the charge here? Right? What fraction of charge is here? So it's not total Q, it's sum of the charge. How can we figure it out? Anybody? Go ahead. Very good. So we will make use of this relation. We will make use of the fact, look at rho. Rho from here can be written, do you see that rho can be written like this? Rho can be written as Q divided by 4 over 3 pi r cubed. But can we also write rho in terms of Q enclosed? Because remember that the charge is uniformly distributed. So what you're saying, if the charge is uniformly distributed, if you tell me write the rho in terms of the total charge including everything, then I'm going to write it in terms of the big radius, which is the total, which will give me the total volume of the sphere. But if I wanted to write rho in terms of Q enclosed, what should I write here? If the charge is uniformly distributed, please.
The lowercase r.
So I'll write 4 over 3 pi r cubed like this.
Yeah.
Exactly, that's absolutely correct, because the point is if the charge is uniformly distributed on the sphere, that means rho is constant. This thing is not changing. It's the same in this region, this region, this region, everywhere. So rho is a constant thing. And that means if you look at total charge divided by the total volume, that is the same as the charge that is enclosed in this little volume divided by the volume of this little sphere. Does that make sense to everybody? Okay, so if that's the case, can we figure out Q enclosed in terms of Q? Because we may know Q, but we don't know Q enclosed. So looking at both of these things together, we can say this for sure. So combining these two, we can say Q divided by 4 over 3 pi r cubed is equal to Q enclosed divided by 4 over 3 pi r cubed. Notice that I can multiply by 4 over 3 pi, that gets cancelled, and what I have is Q enclosed is equal to Q times r cubed divided by r cubed. If that's the case, is it easy to find the electric field then? All you have to do is plug it here. Because this, remember, this thing is working for all of the points, whether the point is inside or outside. Just that for a point outside, Q enclosed will be total charge, Q. For a point inside, you really need to figure out what is Q enclosed, and we just now found it's this. So then, for r less than r, the electric field, which is K Q enclosed over r square, becomes K, Q enclosed is this, Q r cubed over r cubed times r square. Notice that two of these powers of r get cancelled and we get magnitude of electric field is k q over r cubed times r. Do you see r cubed and r squared, two powers get cancelled and we are left with r? Do you know what that says? This is saying that the electric field is proportional to r. Is k constant? Yeah, in SI unit it's 9 times 10 power 9, right? Is q constant? Yeah, you told me how much is the total charge. Maybe it's 10 power minus 6 coulomb, maybe it's 2 times 10 power minus 6 coulomb, whatever it is, you have told me it's some fixed number. Is capital R fixed? Yeah, you have told me what is the radius of this ball, yarn ball. So the only thing that is variable is small r. What is the electric field at the center, folks? What will we have to plug in there? Little r is equal to 0. So the electric field here is 0, absolutely correct. As you go far away, farther and farther away, the electric field will keep. Do you see it keeps increasing? And then when you go outside, it becomes kq over r square, right? Just like a point charge. So I want again all of you to take a second, work with the person next to you, not a second but a minute, and draw a graphical representation of the electric field. What if in the exam I said, which of these 5 things are correct? And they are all showing you some electric field as a function of r for, and one of them is for volume charge distribution like this on a sphere. Okay, so you take the time to work with the person next to you, and I want to see you do this. Everybody should work with the person next to them. All right, somebody from the first row, please. Anybody from? Yeah, go ahead, please. Tell me how it goes inside here.
Starts at 0. It starts going up exponentially until it gets to r, little r equals r.
Okay, it starts going up linearly all the way till r is equal to r, right? Because the thing is, because this thing is like saying, look, this thing is a constant, right? So we can say it doesn't change. So we are saying, it's like saying y is equal to a constant times x. And do you see y is equal to a constant times x is a straight line that passes through the origin. So it goes straight up to here, and then what happens?
And then it starts arcing back.
Very good. It starts falling off as 1 over r square. So here in this region, electric field magnitude everywhere will be k q over r square, and here everywhere electric field is equal to a constant times small r. What is this constant? That constant is this thing, k times capital Q over r cubed. Whatever it is, if I gave you the total charge q, if I gave you the radius of the sphere, you can figure out what that constant is, right? So the point is, it's a linear increase here, and then it's quadratic fall off after the thing. Should it match here? Yes, it should. And let's see if it does or not. So when r is equal to r, at r is equal to r, what happens to this thing? Let's look at it. Do you see that becomes E is equal to k q r over r cubed? And is this the same as kq over r square? And that's exactly what it is if you think about the electric field outside. So yes, at this point there is the electric field coming from this side and this side do match. So this time there is no discontinuity in electric field like we saw in the previous case, but there is a discontinuity in the slope. The slope from outside is this way, the slope from this here is this way, but the electric fields match if you go from inside or outside. Is that making sense, folks? Any questions about this? Okay, so now that we have done sphere of charge, let's deal with another very highly symmetric problem. We are going to deal with problems with cylindrical symmetry now. And the first problem I want to do with you is going to be finding the electric field using Gauss's law due to an infinitely long line of charge. Means it's like a thread, a very, very long thread which you can think of as infinite at a distance r from this thread if the charges are uniformly distributed on this thread. So let's try to figure out now electric field due to an infinite line of uniform charge. So here is the thing. I have this thread, and on this thread there is charge which is uniformly distributed, and this thread is infinitely long, that means much longer than any distance where we are interested in finding the electric field. Let's say the charge is positive. Okay, we have to find the electric field, let's say at some distance r away. This r is the variable. I could ask you here or here or here, here or here, here, etc. So this is my question. Find the electric field at that point. You are given that the charge per unit length lambda, this is the charge per unit length. This can also be called linear charge density. And this is given to you. Maybe this is given to you to be, say, 1 microcoulomb per meter, 10 power minus 6 coulomb per meter or something, 2 times 10 power minus 6 coulomb per meter or something. So that lambda is given to you. In terms of that lambda, you have to find what would be the electric field at a distance little r away from this infinite line with uniform charge. If you were to use Coulomb's law, what would you do? If you were to use Coulomb's law, you'll break this line into little dq's, wouldn't you? You would say, oh, what is the contribution due to this little dq, this little dq, etc. You will do all of those contributions. You would break it into components. You'll choose a coordinate axis, and then you'll find the vector sum to find the total electric field. Now we are saying we want to use an easier approach in which you don't have to do any integrals. You don't have to talk about any decomposition into components. So we want to be able to use Gauss's law. The question is, we can use it. The point is, we need to be careful in choosing our Gaussian surface, in choosing our closed imaginary surface, because we want to choose our closed imaginary surface to be such that we can say the electric field maybe is constant in magnitude everywhere, at least on most of the surface or something, so that we can pull this out. Because we don't really want to do any tough integrals. You know, we don't want to get our hands dirty in doing some difficult integrals, because otherwise what's the point of using Gauss's law? We might as well go back to Coulomb's law, right? And think about little dq's and adding up vectorially the contributions of dq's. So I want everybody to think about think about it, imagine in your head a thread. There's a huge thread from minus infinity to plus infinity on which charge is uniformly distributed. We are asking you to find the electric field at a distance r, perpendicular distance r from the thread. What kind of imaginary surface would you consider that passes through the point where you're trying to find the electric field, such that you can claim that you don't have to do any integral? You might be able to pull the electric field out. You might be able to say, oh, electric field is making angle that is the same everywhere, or easy angles, so that you don't have to do much work. Please talk to a person next to you.
Yeah, the line. Yeah. So it'll be
All right, anybody has any thoughts? Go ahead, please. A cylinder, you know, how might I think of a cylinder? Maybe like a cylinder like this or something? Is this what you were thinking of?
Like a cylinder that, like an infinite cylinder that enclosed the entire line, because the charge would be the same no matter what point it was on the surface of the cylinder away from the line.
Okay, I guess the only problem with something there's nothing wrong with what you're saying, that's perfectly valid. The only thing is, you know, for an infinite cylinder, you know, you can start worrying about the caps, you know, because this surface needs to be closed. So you might say, oh, where are the caps for the cylinder, because we need to close it. So it might be a good idea to consider, say, a finite cylinder, you know, a cylinder with finite length like this. But is this going to be working? Is this something that you like? If you don't like, tell me why you don't like it. It turns out this is the surface that you should choose. This is a good Gaussian surface to choose. Why is that? Because if you think, and of course you should, at the two ends here, you should close the ends. Okay, let's say that the height of the cylinder here is h. Let's say h is the height of the cylinder. Okay, first of all, even before we do anything, one thing that we need to figure out, even before we have used Gauss's law, is what would be the direction of electric field at any point due to an infinite line with uniform charge. So imagine a thread which has charge uniformly distributed on it, and you are saying what is the electric field at some point at a distance r away. Can you tell the direction? Yeah, go ahead. Very good. It will be perpendicular to the line. It has to be perpendicular to the line. There is no other direction. How do we know? Because look, this is an infinite line, you know, and if it's an infinite line, if you're trying to find the electric field here, think about, you know, think in terms of Coulomb's law. If you were using Coulomb's law, you'll start taking the contribution of this little dq, this little dq, this little dq, this little dq, etc. Would you say that there are as many dq's on this side as on that side if this line is infinite? Yes, and hence when you start saying, oh, this is my x-axis and this is my y-axis, if you start looking at contribution of a dq on this side and a dq on that side, they are at equal distance, you would say those two dq's will produce electric field which are like this, which are equal in magnitude, but they point like this. And then when we look at the contribution this way or that way, and then look at the contribution this way and this way, the contributions in these directions cancel out and in these directions add up. Would you say that for all pairs here? If this is an infinite line, you can think about infinite number of pairs on both sides, right? So the answer is the electric field has got to be perpendicular to the line anywhere. So if this is my line, if you ask me for electric field here, I'll say it's perpendicular to line this way. If you're asking me for electric field here, I'll say it's perpendicular to the line that way. If you're asking me for here, I'll say it's perpendicular to the line that way. Here, perpendicular to the line, here, perpendicular to the line, etc. Right? Is everybody convinced about that? Okay, so if the electric field at every point, and notice this is true for every point here, the electric field has got to be perpendicular. Even here, every point electric field has got to be perpendicular. Why? Because I can use the same argument here. I can say there's a dq here, there's a dq here, there's a dq here, there's dq here. They produce electric fields which are, you know, whose x components will cancel out because there are infinite number of points on this side and infinite number on the other side if this line is infinite. Is everybody agreeing with that argument? For an infinite line, there is no problem at all. For a finite line, we couldn't use this argument because for a finite line, if you have a finite line here, this is the end. In this case, the only place where you can say the electric field is straight up is at the center, right? Do you see that you cannot say that the electric field is actually straight up at the end here? Why not? Because think of little dq's. This little dq will have its electric field like this, you know, this is what you can call DE1 for example, and there is another end that will have its electric field going like this. The point is these electric and then there are these things in the middle, these things will not have their electric field components in the x direction cancelling out. So for finite line you cannot say that electric field at every point here is going to be radial, only at the center will be radial, not elsewhere. But that's not what we are talking about. This is not our situation. We have an infinite line, and so for any place you consider, here or here, there are infinite number of charges this way and that way, and so this argument holds. Does that make sense? Okay. So now that we have figured out that the electric field at every point is perpendicular to the line, what argument can you make about how we can use Gauss's law, and we don't want to do any complicated integral. So imagine in your head you have a line here, you have enclosed a cylinder around it, right? First of all, what is the direction of area vector at different points on the surface of this cylinder? Remember, area vector is always perpendicular to the area. For a closed surface it's outward perpendicular or outward normal. So is everybody seeing that the dA here will have a direction that is in the same direction as electric field? The dA here will have the same direction as the direction of electric field. The dA here will have the same direction as the direction of electric field. What about here? Same thing. dA will be the same as the direction of electric field. The dA will be the same. Try to imagine a three-dimensional thing in your head. The point is, if you have a cylinder around, right, at every point on the cylinder the direction of electric field and the direction of area vector are the same. So that means cosine theta is cosine 0, which is 1 everywhere on the curved part of the cylinder. Please.
Why don't we have to think about the electric field at the end of the cylinder?
Which end?
Either end, because wouldn't it be different than it would be
Here? We will have to, and in fact we will worry about it in a second. So let's worry about things one by one. So he is absolutely correct. Let's call it cap number 1. Let's call it cap number 2. This is cap number 2, and this is the curved part. And so yes, it is true that if I'm using Gauss's law says this: integral E dA times cosine theta is equal to Q enclosed divided by epsilon 0, right? And you are correctly pointing out that this closed surface can be broken into 3 parts: the curved part, this cap, and this cap. So this integral can be broken into cap 1 plus cap 2 plus curved part. These are the 3 things times integral E dA times cosine theta, and that's equal to Q enclosed over epsilon 0. Please.
Don't they ignore the caps because the area vector is perpendicular to the electric field vector?
So that's exactly the reason why it will give you 0 contribution. So you really hit at the heart of the problem. So the thing is, it's not that we are ignoring it, but the thing is it is not going to give any contribution at all. So you're absolutely correct, because the thing is, if you look at this cap for example, you know, the electric field here, you know, is like this. The electric field here is like this. Everywhere the electric field is this way. Do you see that? Because that's what we said, the electric field is always going to be the perpendicular to this line. So these are going to be the directions of electric field, but which way is the area vector here? Suppose you look at a little dA, that's pointing this way. If you look at here, dA is pointing this way. So what is the angle between electric field and area vector on the cap? 90. Do you see that? So the point is that for each of the caps, this cosine theta, if you want to do it separately, you can say, you know, cap 1 will be E dA times cosine 90 plus cap 2 will be E dA times cosine 90 plus cap 3, not cap 3 but curved part, and curved part we already said will have the electric field and the area vector in the same direction, so that's cosine 0, right? Not only that, the way we have chosen this cylinder, the axis of the cylinder is the same as the line. And so are all of the points on the curved part equidistant from the cylinder, imaginary cylinder that we chose? They are. So will you say that the magnitude of electric field at all points on the curved part will be the same? It should be. So that means I ought to be able to pull the electric field out of the integral, and I ought to be able to say this is E times cosine 0 degrees on the curved part times dA, and this is equal to Q enclosed over epsilon 0. Do you see that this is 0? This is 0. Why? Because cosine 90 is 0. Cosine 90 is 0. And in fact, exactly what you pointed out, we could have seen this in the picture. Do you see that there's no electric field lines that are penetrating through the caps? They're all grazing through like this. So there's no flux through this, there's no flux through this. So there's no contribution to the flux, because remember, this thing is really the flux. This is really the flux, phi. And so the point is there is no contribution to the flux because no field lines are penetrating through these two caps. The only contribution to the flux is through the curved part. Is everybody agreeing with that? With this? Then at this point we are pretty set, because cosine 0 is 1, this is just 1. So what we get then is E times integral dA. We end up with E times integral dA over the curved part is equal to Q enclosed over epsilon 0. And what is the integral over the curved part? It's just the area of the cylinder. And area of the cylinder of radius r is the circumference of one line, which is 2 pi r, times the length h. So that's just going to be the total area of the cylinder, which is 2 pi r times h, right? This is the area of cylinder or curved part. And so this is equal to Q enclosed over epsilon 0. Now what is Q enclosed in terms of what you have been given? You have been given how much is the charge in each meter, how much is the charge per meter, that's lambda. So we want to get the answer in terms of lambda. Can you tell me how much is the charge enclosed? If the length of this Gaussian cylinder is h, how much is the charge enclosed? Please.
Just h times the length.
Excellent. It's just lambda times h. That's the total charge that is enclosed, because this is the charge per unit length and this is the length. Do you see that? Okay, so if that's the case, notice one thing very important, and this should always happen. H and H get cancelled from the two sides. Do you notice that? And it should, because if you choose a Gaussian cylinder to be longer, like you were saying, I want to choose it to be very large, you know, and there's no real problem except that it is hard to visualize what would be the caps. But the point is, it doesn't really matter who chooses how big of a length for the cylinder, because H cancels out, and what we end up with is that the magnitude of electric field is lambda divided by 2 pi r epsilon 0. This is it, we are done. Electric field due to an infinite line with uniform charge turns out to be have a magnitude lambda, charge per unit length, divided by 2 pi r epsilon 0. R is the perpendicular distance of the point where you're trying to find the electric field, and the direction of electric field is always perpendicular to the line. We already discussed that. Done. Notice that this problem has exactly the same symmetry as, say for example, if we had an infinite cylinder with uniform charge on its surface. Do you see that? So what if I change the problem on you? For example, one of your homework questions might say, try to work this thing out with an infinite cylinder of charge. there is charge uniformly distributed on the cylinder. Could you use the same kind of argument? Yeah, you could. So for example, if you had to find electric field due to a cylinder, due to an infinite cylinder with uniform charge on the surface, so they basically this time what we have is this, we have a really huge cylinder and we have this charge on its surface. This is uniform charge. Okay, let's say that the radius of the cylinder is r, capital R, and suppose I asked you, this is an infinite cylinder, so this goes to minus infinity in this direction and this keeps going to plus infinity in this direction. This is an infinite cylinder, you cannot see its end. Okay, and suppose I asked you, tell me the electric field over here. Will you again say from the symmetry of the situation that the electric field must be perpendicular to the axis of the cylinder again? If I ask you for electric field here, you will say, oh, it must be perpendicular to the axis like this. So imagine in your head you have this hollow thing, hollow tube with charge on its surface. It's infinitely long and I'm asking you what is the electric field here due to all of the charges on the cylinder. It's basically perpendicular to the axis of the cylinder in the radial direction, right? Everywhere? Okay, so if that's the case, again, if I asked you for the electric field here, can you again choose your Gaussian surface to be another cylinder which is concentric with this? So this time your cylinder could be, it will be passing through this point where you have to find the electric field. And again, choose it in such a way, you can choose any length h that you feel like and choose it in such a way that this distance above is the same distance as this. So in other words, this is r, similarly this is r also, right? So the radius of the cylinder is small r, your variable. Is everybody convinced that all of this logic that we have used here will apply even to this case? Right, isn't it? Because again we can say, hey, if you look at these caps, this is my cap 1. If at cap 1 the electric field is always pointing this way and the area vector dA at every point is this way, then I know that the angle between the two is 90 degrees and there won't be any contribution to the electric field from cap 1 and cap 2, right? And again we can say, oh, so the electric field contribution is only from the curved part of the Gaussian surface we have chosen, and again the magnitude of electric field will be the same everywhere because I chose the Gaussian surface to be concentric with my cylinder of charge and every point on this surface is at the same distance little r away. So E can get pulled out. Cosine theta is again cosine 0 everywhere because the electric field will be radial so long as this cylinder of charge is infinite, and so I get the same exact thing, I get the same exact result. So this is the electric field for r greater than r. What about for r less than r? For r less than r, the thing is, what is the electric field at a distance small r away from the axis of the cylinder? This is my axis of the cylinder. How much is the electric field here? How will I do it? Again, will the process be exactly the same? You will choose a Gaussian surface which is a cylinder that is passing through this point. Again, by logic you can again say, hey, due to all of these charges on this cylinder, the electric field at all these points on the cylinders better be equal. The electric field better be perpendicular to the axis, just by the same logic that we are using for a point outside. You could use the same logic for inside, right? we can again go through the same arguments to show that the electric field on cap 1 and cap 2 is perpendicular to dA, and so cosine of the angle is 90. These things drop out. Only thing you're left with is this. Again, you can say the way I chose my imaginary Gaussian surface, which is a cylinder, it was in a careful manner so that the electric field magnitude is constant. I can pull it out. Cosine theta is cosine 0. Same logic applies. We are again back to here, right? The only thing that you need to worry about now is what is Q enclosed. You see, so this point is still good, right? Is everybody agreeing that up to here we could do the same exact argument again? But at this point we can now say, oh, so E times 2 pi RH is equal to Q enclosed divided by epsilon 0. That means E is equal to Q enclosed over 2 pi RH epsilon 0. The question is, what is Q enclosed now? Huh? Go ahead, please. Yeah, it is 0 because if all of the charges are on the surface of the cylinder, then there's no charge here. Q enclosed here inside the cylinder, Gaussian cylinder, is 0. And so the electric field inside will be 0. Is that making sense? So basically, outside the cylinder, the electric field falls off as 1 over r. Notice this is not 1 over r square, it is 1 over r. Inside the cylinder, electric field is 0 because there's no charge enclosed and the distribution of charge is symmetric on the surface, right? Okay, you could have a third case, and I don't exactly remember which problem you have in the homework, but the third case could be charge is uniformly distributed in the volume of the cylinder. What will you have to do there? You see what I'm asking? I'm saying, what if in the exam or homework you have a question that says here is your cylinder, okay, and the charge is not just on the surface, the charge is uniformly distributed everywhere. Right? In this case, how would you do it? So uniform charge in the volume of cylinder, volume of this infinite cylinder. Do you see that if I asked you for a point outside here, again from the same logic you can say to me electric field will definitely be perpendicular to the axis of the cylinder from the symmetry of the situation, right? Charge is uniformly distributed, this is infinitely long. You can again choose your Gaussian surface to be a cylinder at a distance r away when I'm asking you to find the electric field at a distance r away. Do you see that this whole logic again works for r greater than r? Will the charge enclosed again going to be charge per unit length of the cylinder times h? It will be, right? So this result is still good. That result will still be good. This is my h. So for outside it's still going to be good. Is everybody convinced? Okay, what about for a point inside? So suppose I say find the electric field at a distance r away inside. Again, this time you will make the same kind of argument. You will choose your Gaussian surface to be a cylinder. You will work through the whole problem. You are again here. But can you say that this is 0? You cannot say it's 0. So this line will not work. Is everybody convinced that for r less than the radius of the cylinder, you can again go through the same argument? The only thing if this is capital R. The only thing you cannot do is you cannot just say Q enclosed is 0 because it's not 0. This time if the charge is in the volume, there is some charge that is enclosed. Is that making sense? Can we figure out what is the charge enclosed? Yeah, we can figure out in terms of lambda what is the charge enclosed, right? How can we figure it out? Well, I mean, obviously we need to also know how much is the total radius. So suppose total radius is capital R versus small radius, and we will have to figure out, you know, how much of the charge is enclosed. So all you have to do, just like the way we did it for the volume charge, here also you really need to just figure out what is Q enclosed for a given radius R, right? And once you figured out how much is the Q enclosed, you are set. Just plug it here and you have the answer. Any questions about that? Anybody? Okay, then the last case where there is enough symmetry so that you can do Gauss's law and not have to do some complicated integral to find the electric field is problems in which there is planar symmetry. So for example, if you have an infinite sheet with charge on it, and in fact this problem we already did using Coulomb's law. Do you remember? We started with a disk of radius r, and then later we said, hey, if the radius went to infinity, in that case the electric field magnitude becomes sigma over 2 epsilon 0. Do you remember that? And it was straight out perpendicular to the surface if the charges were positive, and straight in if the charges were negative. That will be true here also. If these charges are negative, then the electric field will be radially inward as opposed to outward. Okay? So how do we do that problem that you've already worked on once, for which you actually needed a table of integrals? You needed to take a limit in order to get to the infinite sheet case. Now the question is, can you do it really easily using Gauss's law? The answer of course is yes, because if you have an infinite sheet of charge, you can find the electric field at a distance r away very easily. So let's say that this is my sheet, okay? And on this sheet I have charge uniformly distributed, so that means charge per unit area is constant. Let's call it sigma. Sigma is the charge per unit area. Usually that's the symbol people use. For charge per unit length they use lambda. For charge per unit area they use sigma. For charge per unit volume they use rho, but these are Greek symbols that people usually use, so let's be consistent. The question is, if this sheet is infinite, and again what is the meaning of infinite? Nothing is really infinite, but if you are finding the electric field at a point that's really close to the sheet, it's like being on Earth. If I stand in Pittsburgh outside and I look at the ends, it doesn't look like Earth is a sphere. I don't see the edges of the Earth. Earth almost looks infinite. That's because I am at a point which is very close to the Earth. If you are an astronaut in outer space, then Earth's surface area will not be infinite for that astronaut. In fact, he'll see a ball. He'll see Earth as a sphere. Why? Because he is so far away from Earth that Earth's surface first of all doesn't look flat to him, right? So for me it'll be a good approximation to assume that this is a horizontal surface here. For an astronaut in outer space who's very far away from Earth, that it will not be a good approximation for him to consider the Earth to be a flat surface. Similarly, what I'm trying to say is that it will be a good approximation for some point which is really close to the sheet to think that this sheet is pretty much infinite. On the other hand, if you're over there looking at this sheet you can see the edges. This sheet is not infinite for a point over there. Is that making sense? So you can only assume that this sheet is infinite if you're trying to find electric field at a point which is much closer compared to the size of the dimensions of the sheet. Okay? Alright, so we are going to assume that the sheet is infinite with those caveats in mind when this approximation is a good one. And in this course actually anytime I give you a sheet, you can safely assume, unless I say no, don't assume it's infinite, you should assume in general it is an infinite sheet. Okay? So I want you to take 1 minute, talk to a person next to you and think about what would be a good Gaussian surface. We have to think of some imaginary surface to choose. If I ask you what is the electric field, say over here, at a distance r away from the sheet, this is an infinite flat sheet like this, what kind of Gaussian surface would you choose so that you can use Gauss's law to find the electric field at this point, and obviously that point where you're trying to find the electric field should be on the Gaussian surface, this imaginary surface you choose. But think about choosing that surface carefully so that you don't have to do any complicated integral. You can pull the electric field out, you can claim that electric field angle that the electric field is making with area vector is either 0 degree, 180 degrees or 90 degrees, something simple so that you can do your things, your integrals, without really doing them, without really going through some mess. Talk to a person next to you. Alright, who wants to help me? Anybody? Any help from anybody? Suppose I wanted to find the electric field, say at some point, you know, let's say over here, at some distance, some perpendicular distance away. How do I do it? Any thoughts, folks? Go ahead, please.
You could use a cylinder where that point is like on one of the caps, and then you have the other cap on like the other side of the sheet.
Actually, that idea is an excellent one. In fact, in this case, you have many choices for Gaussian surfaces. It's not like the case with the spherical symmetry or the cylindrical symmetry where there aren't that many good choices. You know, here there are many good choices, and one of them is exactly what you said, which is if suppose I have to find the electric field here, I can think of a Gaussian surface such that half of this surface is behind this sheet and half of it is in front, right? That's what you were saying? Is this what you were saying? Yeah, that would be a very good choice. So, and in this case, again, before we do any calculation, one thing, so basically here is what we are talking about. So this is my sheet, this is my infinite sheet. I have to find the electric field over here. What I do is I choose a Gaussian surface such that that point is on a cap, and then I have a cylinder like this, and equal amount of cylinder is on the other side as well. Okay? If that's the case, one thing is, if this sheet is infinite, will you say that the electric field is perpendicular to the sheet? Again, think about using Coulomb's law and breaking it into little dq's. Wouldn't you say that if this sheet is infinite and you cannot see the edges, the electric field must be definitely perpendicular to the sheet, right? This time, what would be the contribution of the cylindrical edges to the flux? This time it will be 0, because if you think about the cylindrical side, do you see that the cylinder here, this part of the cylinder, the area vector will be like this, and the electric field now is like this. So this time what you will see is there's no contribution from the cylindrical side, the contribution is only from the caps, and we will talk about it next time. Have a great weekend, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.